Hello class, we are on to the last section of chapter 9. This is chapter 9.6. We're going to talk about equations of lines and planes. Now you might say to yourself, Professor Williams, we've been doing equations of lines forever. We already know how to do lines. That's true, but today we're going to talk about lines in 3 dimensions, right? So we saw before that when we talk about a line in 2 dimensions, it's pretty much analogous to a plane in 3 dimensions, right? So then that brings us to the discussion of like, well, how do I talk about a line in 3 dimensions then, right? So that's what we're going to talk about. So we're just working more in 3-dimensional systems today. And so we're going to talk about lines and planes. So in R2, if we want to create a line, we need to have a point, a starting point, either that's on the y-axis, which we call our y-intercept, or it's some other point in space, right? After that, I need to know a slope. If I have a starting point and I know my rate of change, I know what the slope of my line is, I can find any other point on the line if I have a point to start with and a slope, right? Sometimes we find the slope by having 2 points. If I know one point and another point, I can find the slope between them and then find any other point on that line, right? So I need a point and a rate of change, basically. In 3 dimensions, it's somewhat similar. I need to have a point and a vector, right? A slope is not enough, just knowing the rate of change, because now I have a whole 3-dimensional system where I can have that point, and I need to know, okay, well, does it change? Is the rate of change in this direction or this direction or this direction or this direction, right? Because I can go up 1 and over 2, but which way do I point when I do that, right? So I need a point and a direction, right? So remember what a vector is. A vector has a length and it has a direction. Its length, we know, is basically the same thing as a slope. So a vector tells me a direction and it tells me actually the rate of change as well. So I need a point and a vector in R3 to make a line. Okay. So let's start with the fixed point, which we will call P naught. So remember, we're in 3 dimensions, so it's x naught, y naught, z naught for this point P. So this point is fixed, meaning it does not move, right? It is a point given to me in space. It's the point that I need my line to go through. It doesn't change, okay? So let's take a secondary point anywhere on my line, right? I ideally would like to have a direction that I'm going, right? So I know my line needs to go through this point, and then I can choose any other point that I need my line to go through, okay? We will call this P, X, Y, Z. So notice that this does not have a subscript, 1, 1, 1, or 2, 2, 2, or what have you. So these can change because it's an arbitrary point, okay? So let's say that V is the vector that's formed with P naught as my initial point and P as my terminal point, okay? So then now we have a direction. So we have a point and we have a direction. So my vector V is going to be x minus x naught, y minus y naught, z minus z naught. Okay, so R naught is the position vector that is formed by our fixed point and the origin, right? So we know that we can consider a vector when we place it at the origin as it's easier to work with, right? So it has an initial point of 0 and a terminal point at x naught, y naught, z naught. So we can just call R naught as that initial position vector, basically, right? So it tells us that initial point, that fixed point. Okay. R is that secondary point. Okay. So it's from the origin to P. So we represent R with X, Y, Z. Okay. So V then is the vector that connects the tip of our R naught position vector and our generalized position vector R. Okay. So this is our initial point, P naught, it's fixed in space. The vector that points to this point is R naught. Okay. If we choose a secondary point in space anywhere along the line that we are choosing to create, we have a vector R that terminates at that point as well. Okay. So the vector V connects those 2 points. So you can see here that r naught plus v is actually this vector r. Okay, and so our line then goes through this point and points in the direction of v. So that's how we create a line in 3 space. So r is given by r naught plus v, right? R naught plus v is r, and the line goes through our fixed point r naught, okay, the terminal point of r naught, and the terminal point of r, and r moves, right? R naught is fixed, but this point could be any point in space. This point stays, this point can move in this direction, it can move in this direction. So it changes over time, okay? Time is generally represented with t. So we can rewrite this as r equals r naught plus tv. So again, if r is here, this is my length of the v. If r is here, well, v is shorter, right? And my r vector is shorter. If my point in space is out here, my v vector will be longer, and so will my r vector. So v changes over time, and so does that position vector r. It also changes over time. So r varies with time, and r is actually what we want to get out. Any point on our line is given by r. So r equals r naught plus t times v. Okay. So again, notice that v is also a scalar multiple of time. So if we break this down into its components, right? So we break r down component-wise. It's x naught, y naught, z naught plus t times v1, t times v2 plus t times v3. And if we actually just go ahead and add these together, then the point xyz, or r, right, is given by x naught plus tv1, y naught plus tv2, z naught plus tv3. So this breaks down the components of my position vector on my line, right? So x is given by this value, y is given by this value, and z is given by this value. So that's lines. So now let's talk about planes. So a plane is a 2-dimensional space in 3 dimensions. It goes on forever in the upwards and downwards position, and forever in the left and right position. However, if this is skewed, our understanding of left and right and up and down is a little bit different. Okay, so again, just think about it as like a flat piece of paper. However you can hold a piece of paper in space is how we'll represent a plane. Okay, so if I want to talk about the equation of a plane, very similar to what I had before, instead of a point and a vector, I need a point and a specific vector. I need a vector that is orthogonal to the plane. Because if I have a vector that's orthogonal to the plane, then that means that any other vector that's inside of my plane is orthogonal to that given vector. Okay, we call this vector a normal vector, or n for short. Okay, so the vector I need is n. It forms a right angle with any vector in my plane, and I have a point in my plane. Okay, that's all that I need in order to create a plane. So let P naught be x naught, y naught, z naught, be a point that's in my plane of interest. Okay, then a vector from any arbitrary point to my P naught has the form of x minus x naught, y minus y naught, z minus z naught. So very similar to that z that we had before, right? I'm sorry, the v vector we had before. Okay, so yeah, it's very similar to the v. So again, v would be r minus r naught, right? So let's come back here. If I needed to solve for v here, right, I would subtract r naught. R minus r naught is equal to v. So same setup, right? I got my fixed point, I got a generalized point, v is the vector between them. If I want to know what v is, that is the difference between these two values, right? It's two vectors. So n is a normal vector to the plane. So again, it's orthogonal to every single vector that's in that plane. So the dot product between n and this vector v, or p to p naught, is going to be the same as n dot product with r minus r naught, or n dot product with v, okay, which should be 0, because v is in my plane, right? My point p is in my plane, p naught is in my plane. That means that vector v is in my plane, and n is orthogonal to that plane. So we can say that n is ABC. Then the dot product between n and v equaling 0 gives me this equation. Okay, so I already know what v looks like. This is my n. The dot product needs to be 0. This will give me my equation for a plane. Okay, so it's, again, important to remember the process rather than just the formulaic approach or the formula. The formula will help, but if we understand how it's created, it will be a lot more useful to us, right? So this is my normal vector. This is my point, x naught, y naught, z naught. X, y, and z is just some generic other point in my plane. So x, y, z will remain as x, y, and z. Okay, so if we do this dot product, we get a times x minus x naught plus b times y minus y naught plus c times z minus z naught. Okay, so if we collect all of the actual values, the constants, which are x naught, y naught, and z naught, multiplied times a, b, and c, okay, then we can call that just a new constant. Okay, so again, this vector has actual values. X naught, y naught, and z naught are values. X, y, and z remain as x, y, and z. They're variables, right? They change over time. They represent any other point in my plane. So I'll take all my variable terms, once I expand this, and I'll just give it a new, all my constant terms, and I'll just call it a new constant, which I'll call d. So that gives me a times x plus b times y plus c times z plus d equals 0. Okay, and this is the equation of a plane in 3 dimensions. So we've seen this before. I have my r naught, which terminates at p naught. I have my r, which terminates at p, some generic point in my plane. So that means that if p naught and p lie in my plane, then v has to lie in my plane as well. Okay, n, which is orthogonal to v, will be outside of my plane, okay, to form a right angle with v. So my plane is any vector in this space, extend this way, extend that way forever, and n, wherever I move this n up, down, left, right along my plane, it'll always form a right angle. Okay, so any vector in here will always form a right angle with n. So that's all I need for this. So again, remember, n is my a, b, and c. Any other point in here is x, y, and z, and d is formed by collecting the constants, right, with that dot product. So if you need to remember anything, remember this equation for d, but it might be easier just to do this from scratch each time. Okay, so let's do an example, because I know this is all very abstract. So let's do an equation where we find the equation of a line and we find an equation of a plane, right? So find the equation of the line that contains the point 1, negative 2, 1 and negative 3, 0, 2. So one of these is a fixed point. One of these is a terminal point. It doesn't really matter, right? But the difference between these two values would be my vector v, right? So I have one point in my plane, another point in my plane. The vector that starts at one of these and terminates at the other is my vector v, and then I can put that into my equation, because one of these would be r naught, one of these would be r, the distance between them would be v, and so I would have enough to create my equation of a line. Okay, so we want to find, after that, we want to find the equation of the plane that contains this line that connects 1, negative 2, 1 and negative 3, 0, 2, but also has the point 2, 1, 0 in it. So think about a line. A line is dimensionless, right? It goes in forward and it goes backwards, but that's it. I can find an infinite number of planes that pass through any one line unless I have a secondary point that also, or I'm sorry, a third point that also lies inside of the plane. So in order to create a plane, I really need 3 points. 2 points is not enough, because you could just think about a piece of paper that's like spinning, right? There's all different ways for you to create a plane through 2 separate points, or that's centered across a line, right? I need a third point for me to say, okay, this is where that plane has to go through. So First, I'm going to find the line. I can't find a plane through the line because there's an infinite number of planes that go through a single line in space. So you can also think about, like, if you had a piece of string and you tied it up, it's just a piece of string, right? If you put a piece of paper on there, you can rotate that piece of paper around that string as much as you want. So there's an infinite number of planes around that string, right? So if I have a third point, then that's when I can like fixate my piece of paper and say, this is my plane in space. So that's why I need a third point here in order to find the equation of a plane that goes through this line and also this point. Okay, so we know that R is given by R naught plus T times V. I know how to find V. I know how to find R naught. I just need to consider one of these points as my initial point. And I finish out this equation to find R, right? So let's go ahead and use the first point as R naught. That's the easiest thing to do, okay? Plus T times, and then I just need to find the difference between these 2 points. So -3 minus 1, okay? 0 minus -2, and 2 minus 1. So that gives me my V. I multiply it times T. I choose one of the points. It really doesn't matter which one I choose to be my initial point. So I chose this one as the initial point. So this is my R naught. I just finished writing out this equation. Okay. I find my vector V. So I have R naught plus TV. And then I can multiply these things and combine them together to get my 1 minus 4t, my X, all of my Y's, and all of my Z's. Another way to think about this, X is a function of T, Y is a function of T, Z is a function of T. You've basically created a parameterization of a line in 3 dimensions, right? My X is an equation in T, my Y is an equation of T, my Z is an equation of T. So we've basically done is created a parametric equation for a line in 3 dimensions. Okay. Okay. So the equation through the line that goes through the points of 1, -2, 1 and -3, 0, 2 is the vector 1 minus 4t, -2 plus 2t, and 1 plus 2t. So if we want to find a vector that's normal to the line and our new point, right, which is 2, 1, 0, we first need to find the vector that connects the point to either of our other given points. So, okay, so far I have a point and a point. I do have one vector, but now that I have a third point, it'd be nice to find a second vector because I need a vector that's normal or orthogonal to every single vector here. So if I only have one vector, it's going to be hard to find a second vector that's orthogonal to it. But if I have a second vector, especially if I have another point, right? So one vector, I have a third point, so I can create another vector, either from that point to this terminal point or from this point to this initial point, 1, -2, 1. So most likely what I'll do is I'll go from 1, -2, 1 to my other point to find the equation of a vector in the plane. Then I can find the cross product. I have one vector in my plane, which is from 1, -2, 1 to -3, 0, 2, which is that V vector, this -4, 2, 1. Then from this point to this point, I can find another vector, take the cross product of those two vectors, and I will have my normal vector. And then I can go through all this stuff that I did over here with the dot product and these equations. Oops. Let's go back one. Okay. I can take my normal vector and take the dot product with this in order to find the equation of my line. So what I need to do first is I have a vector V. I have another point, so I need to find a second vector and then take its cross product with the vector V. Okay, so that's basically me explaining what I was doing here. So once we do this, we find an orthogonal vector n by finding the cross product. So I already have one vector in my plane, which is -4, 2, 1. I'm going to find a secondary vector u, so I'll use 2, 1, 0, 2, 1, 0, and my initial point, which is -1, -2, -1. Okay, 1, negative 2, 1, sorry. So 1, negative 2, and 1, right? I'm subtracting them to find my u vector. So now I have two vectors on my plane, v and u. I'm going to take their cross product, so ijk, v, and u. And then after I find this cross product, I will have my normal vector, right? So we start with I, we cross out column, cross out row. 2, 1, 3, negative 1 is the resulting determinant. Negative j, negative 4 and 1, 1, negative 1, that's the resulting subdeterminant. And then we have k, and then this is the resulting 2 by 2 determinant we have to find. Okay. So here we're going to have I times negative 2 minus 3. Okay. Here we have negative j with 4 minus 1, so negative 3. And then here we're going to have negative 12 minus 2, so negative 14. Okay, and this was, I skipped it, but negative 2 minus 3 is minus 5. So my normal vector is negative 5, negative 3, negative 14. So I'm going to take this now, and I'm going to dot product with, basically with my r, the equation of my line. Okay, so the only problem with that is that it's in terms of t. So coming back to this formula, I really need x minus x naught b. Let's go back. I have my normal vector. I need x, y, and z. Okay, not t's. So I'm gonna pick a point that's in my line or in my plane. Probably, it really doesn't matter which point I use, honestly. So let's go with the first one, which is 1, negative 2, and 1. We'll keep the x, y, and z, and we'll find the dot product with that normal vector we just found. Okay. So let's get to where we are. So we found the normal vector. Okay. For equation of the plane, we can use any of the 3 points that are in our plane. We'll just go ahead and, well, I guess let's use this one. Okay, we'll use the one that we have in front of us. So the equation is normal vector, dot product with x minus the first point, y minus the second point, z minus the third point. Okay. When I take this dot product, so let's expand this n to write it in terms of its components. It looks like this. So I have negative 5 times x minus 2, negative 3 times y minus 1, negative 14z, right? So negative 5x plus 10 plus a negative 3y plus 3, right? Minus 14z equals 0. All the constants I collect and I either throw at the end or I can throw on the other side of the equal sign. It doesn't really matter. I know standard, we wrote it as equaling 0 here, but to be honest, most people will write it as equals negative d, right? They'll move the d over and just have your x, y, and z stuff equaling a constant. That's really the standard form that people tend to write equation of planes in. So here we go, right? Negative 5x, my 3y, my 14z, 10 and 3 give me 13, so I move it over. So you see how it's a little bit easier just to think about, okay, I need this equation, I need my normal, find the dot product, constants go on one side, x, y, and z's go on the other, right? What if we use a different point, right? I said it doesn't matter what point we use, so let's just test that. So we use 2, 1, 0. Let's say we use one of the other 2 points that we had, 1, negative 2, 1, or negative 3, 0, 2. So I think I used this one at the end of this, so let's just go ahead and look at that. Okay, so what if we use one of our other points instead? Let's say our initial point, right, that we used for r naught. So we still have that normal vector here, and we're taking the dot product with the same equation, x minus the first term, y minus the second term, z minus the last term, setting it equal to 0, right? Take that dot product, so negative 5 times this, so negative 5x plus 5, negative 3y minus 6, negative 14 plus 14. Okay, let's go ahead and collect all our constants. So we have 5, negative 6, and 14. So 5 and negative 6 is negative 1, plus 14 is 13, and we get the exact same equation that we just had. Okay. So if we needed to, we could verify this again with our last point, but I mean, I've already done it twice. So if you want to, go ahead and verify this with the last point that we have. But any point in our plane will satisfy this equation because this is the equation of our plane. Thank you.